Welcome to the channel of Sharp Careers. Today our topic is torque on a bar magnet in a uniform magnetic field. Dear students, सबसे पहले हमने यहाँ पे आपको दिखाया कि एक यूनिफॉर्म मैग्नेटिक फील्ड जिसको हम बाय इक्विडिस्टेंट पैरेलल लाइन से हम रिप्रेजेंट करते हैं, जैसे हमने यहाँ पे दिखाए हैं पैरेलल लाइन्स। इन पैरेलल लाइन्स से हम इस बी को यहाँ पर रिप्रेजेंट करते हैं। इस यूनिफॉर्म मैग्नेटिक फील्ड में हम एक बार मैग्नेट को जहाँ पे प्लेस करते हैं, दैट इज हियर शोन इन फ्रंट ऑफ यू एंड सच दैट इट सबटेंड्स एन एंगल। अगर यहाँ इसका डाइपोल मोमेंट है, दैट इज मैग्नेटिक डाइपोल मोमेंट m, दैट इज फ्रॉम साउथ टू नॉर्थ एंड इट सबटेंड्स एन एंगल थीटा। इट इज हियर द एंगल थीटा यहाँ with the direction of the magnetic field. See here, look here, it is here the m is here from s to n, it is here b, so this is the theta. This is here the placement of the bar magnet. इसका साउथ पोल यहाँ पे, इसका नॉर्थ पोल यहाँ पे, और इसकी मैग्नेटिक लेंथ दिस इज हियर 2l. अब अगर हम यहाँ पे इसको दिखाएंगे बाय लाइन डायग्राम, तो दिस इज हियर योर s, दिस इज योर n, this is here the force Fm, that is equal to, by definition, B, the product of B, the magnetic field, and the pole strength Qm. It is here for the north pole, and the magnetic force that is experienced, because it will be here directly in this direction, because north pole will move in this direction and south pole will be attracted by this north pole that is somewhere here, which produces this the uniform magnetic field. So यहाँ पे जो है, it will be here the Fm. Fm is again Fm जो है, Fm is here equal to B into Qm, the pole strength. Look here, there are two forces acting on this bar magnet. One is this force Fm shown here, another force is this here Fm. They are in equal and opposite direction but with different lines of action. That means net force अगर हम इस बार मैग्नेट में देखेंगे, that will be zero, because this Fm and Fm, they are same in magnitude, opposite direction. That means the net force acting on the bar magnet is zero. But due to their different lines of action, remember the line of action is here, it is for this is line of action is here, and this is here the line of action for this is here. So they are different, and because of this, they constitute this. This is the suitable condition for constituting the couple. So the couple means that two equal and opposite forces are acting on a bar magnet with different lines of action. So they will tend to rotate this bar magnet like this. This is here how they will rotate in clockwise direction like this. And we have to see here this rotating effect. This is here measured by means of a torque. So the turning effect is measured by means of a torque. So the torque here is given by torque that is experienced by this bar magnet when placed in a uniform magnetic field is given by, it is equal to force, magnitude of either of the force, into force arm. It is by definition, and this force is here Fm, and this torque is represented by tau, into force arm means perpendicular distance between the two lines of action. So this is one of the line of action, this is another line of action. So we draw a perpendicular that we name as Z, NZ as a perpendicular. So we call this force arm as NZ here. So from this triangle, if this is here the theta, from this triangle S and Z, see here NZ, the perpendicular divided by hypotenuse S and S or Sn, that is equal to sine of theta, or NZ is equal to Sn into sine of theta. So we write here this as Fm into, what is this NZ? This is Sn sine of theta. From this triangle, it is from this triangle SZN. Or you can write in the from this Sn, what is this Sn? This is nothing but this is the magnetic length. So you can write this as Fm, you put the value of Fm. What is Fm? This is B into Qm. For Sn, you put the value 2l into sine of theta. Now see here, look here, this quantity qm into 2L, this is again the product, and this is here by definition equal to the magnetic dipole moment. So you can write this as tau is equal to B into m sine theta. As we have already discussed in the earlier class, that means in 11th class, we have discussed the cross product of two vectors a cross b is equal to ab sine theta with the unit vector that gives us the direction. So it is here the magnitude. So you can write that this tau in vector form is equal to m cross b. What is that equal to? This will be again equal to bm sine of theta with the direction unit vector. Now what about the direction of the tau? This is here again clear that the direction, this is your torque experienced by the, now this is the torque experienced by the bar magnet when placed in a uniform magnetic field. Now what about its direction? Direction of torque tau is given by right hand thumb rule. So what is that? That is here perpendicular to the plane containing M and B. Look here, it may be either like this or it can be like this, depending upon if this is here M, this is here B, M cross, this is M cross B, M cross B. So it is here B cross M. M cross B means it is like downwards, so it is for this M cross B. It is here M cross B. This is M, this is B. So you keep like, it is like this, it is inverse. Inverse is given by this. This is the direction tau. So this is here B cross M. So it will be here in the upward direction. So this is the tau. So this is here how it is here upwards. You keep like this. So this is here, you keep your fingers like in this direction, you keep the fingers in this direction. So this is your direction of this. Now what about the special case of this torque experiencer? We have here, look here, we have the magnitude again. We write here the tau, the magnitude, the torque experienced by the bar magnet when placed in a uniform magnetic field as tau is equal to mb sine theta. Special cases, if number one, if theta is equal to 0 degree or it is 180 degree, tau is equal to 0, because sine of 0 is 0, sine of 180 is 0. So theta is equal to 0 degree corresponding to this position. We have the position of the bar magnet as, we call this position as stable equilibrium position. Stable equilibrium position. And corresponding to theta is equal to 180 degree. Again the torque experienced by this is 0. We call this as unstable equilibrium position. Unstable equilibrium position. Kiski unstable equilibrium position? That of the bar magnet. Number 2, if theta is equal to 90 degree, we have tau is equal to mb only, because sine of 90 degrees 1. So this is here the maximum value corresponding to maximum. Tau is here maximum. Tau is maximum. So this was all about the torque experienced by the bar magnet. Now here in terms of the torque, sometimes we have to define the magnetic moment. The definition of magnetic dipole moment, what is that equal to? If you want to define magnetic dipole moment, since tau is equal to mb sine theta, if theta is equal to 90 degree and b is equal to 1 unit, then your m is equal to tau. So you define the magnetic dipole moment as the torque experienced by the bar magnet when placed at an angle 90 degree to the magnetic field of unit strength. So this was all about the torque experienced by the bar magnet when placed in a uniform magnetic field and the definition of magnetic dipole moment in terms of the torque experienced by the bar magnet. Thank you very much.